everyone, and thank you for joining Oberon again. I'm here to proceed with my explanations of the Feigenbaum module, which is a first example of a full-fledged visual gadget. And I hope you remember the last time I told you something about the type which we call fractal and about type extension. Just a little repetition here. I showed you this data structure here, which is a record derived from the base type gadget's frame description, and I showed you all those variables here. Let me add just one thing I want to emphasize again, because this is really crucial. Every time you want to specify a variable which has to be accessed from the outside of your module, please don't forget to provide this asterisk sign here behind the name. Everything that has an asterisk sign here is going to be exported to the outside of your module. If you do not so, if you leave out the asterisk sign, this variable can only be used internally. Okay, please don't forget this. Okay, so today we're gonna touch a very crucial point, the messaging system. So what is a message? I told about messages sometimes before in my previous videos, and now we gonna take this thing by the head and let's look in the Oberon Companion, chapter 5. There is a good example about what a type is. A type the message is. See the subchapter 5.6. Every one of you who has a native Oberon system installed on some platform has access to this information. So let's start here. As you can see here, a message is based on a very basic type named object message. An object message just contains two fields, a stamp and a D-link field. A stamp field is something like a timestamp that makes it possible for the message receiver to see if a message is doubled, so you can distinguish it by the timestamp. And D-link is object link, where you can provide a link to the object you want to target or this message is coming from. So let's leave this by side for the moment. The more interesting part is frame message. Frame message you can see here is a record that is derived from the base type object message. So this here is a type extension from this type here, and you can see that it provides a frame type variable, and two types, x and y, that are integer values. So the conclusion is near that these are some kind of coordinates, and res is standing for result, so it's possible to send the message back with a result. So this is a very easy structure. There are some more message type, in fact there are dozens of them that are a bit more complicated, but frame message, because this is a message for a very basic visual gadget type, is also pretty easy. Okay, for example, you can see here the caret message. This is a message structure for dealing with a caret, namely with a cursor you can place somewhere in a text area, and you see it is containing a few more fields, but we will leave this on the side for now. Okay, so let's go back and before we dive into the message handler, I want to start with the procedure that rebuilds our gadget, and it's named new. I hope you remember in the last time where I showed you the interaction between the panel and the fractal gadget, that every time our panel is invoked, it also uses the new procedure to rebuild the fractal gadget. And this is what you can see here. This is a new procedure. So when it is invoked, following things do occur. First, you can see here a variable of type fractal, with the type we specified at the beginning of the of our module. That means this type here, the fractal type, is declared here, and then a new operator is invoked with the parameter of our fractal. So this is essentially the same what the new operator does in the C programming language, for example. That means memory space is allocated for this structure. It's still empty, but now it is existing because it has a structure in the memory. And some basic fields are also filled with information. Here you can see the width. Is the W parameter is filled with the value 200. That means we have a value, we have a frame width of 200 with a frame height of 115. Here's some information for the amount of dividers we want to use, what is the left value, what is the right value on the x-axis, stuff like that already is filled in here. And we won't go through all the details here because it's not so important. Here a new array is specified for the color plots. And here some very interesting things do occur that are essentially the same when you do your own gadgets. One is that a handler is allocated. So we have a data field here that is named handle, and we assign it to a procedure. So this is a procedure allocation. You can see that Oberon here sees a procedure as a type. You can handle a procedure like you can handle every type, like an integer type or a Boolean type. You can assign it to a variable. This is very interesting. That makes it possible to assign a procedure to this data record named fractal. And this is contained in this field handle. Then we can give it a name. We use the function gadget's name object. Takes the variable name, which is C of our fractal, and name it with a name fractal screen. This is what you can see when you are starting Columbus Object Inspector and you dig into all the informations of our fractal. Then you can see the name of the fractal is fractal screen. This is done here. And then, last but not least, this is very important, you can see that our variable, which is now instantiated and filled with information, is assigned to something that is called object's new object. This, in fact, is a global variable that Oberon uses to manage the gadgets inside the gadget system. For example, when a gadget is instantiated, when it's moved, when it's swallowed by some container, every time this global variable is used. So it's very important when you instantiated your new visual gadget, whatever name it will have, then assign it to this global variable, object's new object. And then we call gadget's update, which just means that the gadget is forced to redraw itself. Okay, now we want to take a look into the handler. And the handler is starting here. The procedure is named handler. It has an asterisk sign because it cannot be accessed from the outside if you don't provide this asterisk sign, as I told you. And here the parameter structure is always the same. It doesn't matter what type of visual gadget you are programming, the parameter must always contain an object and an object message. And very important here is the var specifier. What does var mean? Var means value by reference, variable by reference. The other possibility would be val, which not has to be typed explicitly because it's the default state. When you write nothing here, then you have an invisible val in this position. Val means parameter by value. Parameter by value means that a copy is made and inserted into your function and then worked with. The other way, this is just a reference. It means it's a pointer. This is very essential when you want to do changes on the object. When you want to do a change on the object of the variable fields, then it's essentially that you have a pointer to it. Otherwise, you only would get a copy, and if this procedure is terminated, then the copy is destroyed and all your changes are lost. So this is just meaning. The meaning here is just that you're getting this object message as a pointer. Okay. Then we have something specified here, which is called display3mask. I will come to this point in a few seconds. And we have some integer variables here. Basically, the structure of a handler procedure is always the same. I really was scrutinizing all those different handler procedures in all those example stuff I found in the Oberon system, and I can really say the structure is more or less always the same. Sometimes some parts of the structure are done in substructures or in sub-procedures. Sometimes it's all done in one procedure, but the structure itself is always the same. So you can see that as a blueprint and copy it for yourself when you're doing your own gadgets. Okay, what's happening now? Let's see what is written here. With f colon fractal do. What does this mean? This means we have a parameter f, which is, as you can see here, is an object. Object is the most basic data type you can get in Oberon. Okay, but because this is a basic data type, an object can be far much more. It can be everything which is higher in the object hierarchy than object itself. So when this object is passed as a parameter here, Oberon really does not know at the beginning what type is really meant here, because everything is an object. So here set with f fractal, that means treat f not only as an object, f is of type fractal, which we specified, as remember, here. So it's not just an object, it's a fractal type. So now Oberon knows this is a fractal, and then we dig into this next line. This is a field of the object message. M is the object message, F, as you remember, that was in here. This is this F of the frame message type. This is the frame the message is intended for. That means it's our fractal, because our fractal is derived from the type frame. So that means, sorry, I lost the line here. No, sorry, we have to proceed here. If M is frame message, so here you have the same thing like I told you here, because the message you are specifying here as a parameter as an object message, this is also a very basic type. So also all types that are inherited from object message also are object messages. So again, we have to emphasize here that this is not only an object message, it's a frame message, which is a message type that is derived from object message. Okay. Now, as the system knows, we have F, which is the fractal, we have M, which is a frame message. We look for the destination frame. If this is nil or is identical with our fractal frame, then we do something. This part here should be obvious. Means if the identifier of our own fractal is identical with the identifier in our message, then this message is intended for our frame. This here is not so obvious because here the frame is nil. This is an indication that the message can also be a broadcast message. So that this here is directly intended for our frame. This here is a broadcast message. This is intended for every gadget in the gadget space. So for this we have to look for those both information before start doing something. Now things are becoming a little more complicated. We use these x and y variables to calculate, recalculate the coordinates. So what coordinates do we have here? You can see that the message itself contains an x and a y parameter, and also our frame contains x and y data fields. So what's happened here? Well, the fact is that the x and y parameters contained in the message are the coordinates of the surrounding container frame. In our case, this will be the panel where we added our gadget in. But this could also be, for example, the whole screen itself. This is the origin we have to calculate our new coordinates from, the surrounding container, and then we add the x and y coordinates of our gadget into it, because our gadget has a position inside the container frame. And what comes out here are absolute screen coordinates. Now this is really something that I have to explain. So when you are used to programming something of visual gadget programming in other operating systems, then you have something like this. You have a screen, and this screen have coordinates. Normally they start in the upper left corner, and you have your own window or gadget, and also has some start coordinates. Let's call it x and y 0. So if this is established, all the drawing and plotting you can do here, rectangles, circles, stuff like that, all these coordinates here are only related to the coordinate system of this frame you generated. That means you really do not know where the gadget or this window actually is on the screen. If it's on this side, if it's on a virtual desktop, on another side, it doesn't matter, because the complexity of what's going on when you specify a point, and you say, okay, I want to set this point to black, and I set this in this coordinate x1 and y1, something or some process must existing that derives or this takes this point and moves it down the hierarchy to finally find out where to put it in the memory of the graphical hardware, where this point has to be set. So there are several levels of abstraction between what you're doing and what's actually going on in the hardware. You have, for example, the API functions here of your programming language. You have low-level drivers, you have high-level drivers, you have the operating system itself as a hierarchy level. So all this is hiding the complexity of transferring this point from the coordinate system of your gadget to the video buffer. In Oberon it's much simpler, but this is the reason why you first have some problems to understand it. In Oberon, when you're specifying your gadget and you're placing coordinates here, placing points here at special coordinates, you're using a module that is called module display 3. Display 3 is a module that is not abstract like in Windows or Linux or even more Mac OS, where it contains several levels of hierarchy that disguises the complexity of the system for you. Module display, in fact, is hovering just a few millimeters above the video hardware. Display 3 doesn't know anything about your gadget. It doesn't know anything about your internal gadget's coordinates and what you're doing there, because display 3 just works directly on this screen here. This is where the module display 3 lives, and all the coordinates it takes are absolute coordinates, not relative, absolute coordinates of the screen. And this even more because the Oberon screen, as I told you, is divided into 4 different desktops, but they are managed as one huge big screen with a unique, comprehensive coordinate system. So, and that means the way display 3 works is that it knows you want to show something on the screen that's named your gadget, and it calculates a mask deriving from the origin of this gadget and the start coordinates. It calculates a mask that's covering this area where your display is going to be drawn. And it specifies this mask as a clipping port that ensures that no drawing operations here can go through the boundaries of this mask. And this is done directly, you can say almost directly on the video hardware of your system. And this is why you have to deal with a mask, which normally in other operating systems and other programming languages would not be necessary. So now back to our code. Okay, now we know that essentially the origin coordinates of the fractal gadget are new calculated, also the width and the height, which are just copied from the respective fields from our fractal record. Okay, and then is checked if the message is a display message. Display message is a message that is sent to an object to say, now make yourself visible. Okay, and here's again an if clause that asks if we have a full display message or this here has something to do with the broadcast again. And then a function is used provided by the module gadgets. The function or the procedure is called make mask. And make mask takes the pointer to the frame, the new calculated x and y coordinates of the fractal gadgets, and this is a link to the object that sent this message. And R is this variable here. This is a display 3 mask. This is more or less a structure where all those data fields where we just were talking about with the coordinates are inserted. And then this new mask, which specifies the constraints of the border, the visual borders of our new gadget frame, are used as a parameter for a procedure that's called redraw. And redraw does all the drawing that's necessary to make this frame visible with all its contents. But this is part of the next video, because this would be too much if we would cover this topic also in this video. Okay, and here we have an else if fork with something similar. This is a piece of code that the system is running through when the gadget is moved on the screen. Then also again the mask is recalculated by use of another function, the function adjust mask from display 3, and then again we invoke our redraw procedure. Okay, but as I said again, this is stuff for next video. And this is basically everything that's necessary to handle the display message. We have some message types more. You can see we also have an input message and modify message, control message, stuff like that. As you can see here, we're actually only going to do nothing with it, but nothing is not really true. We forward this message M to the Gadget's frame handle. Gadget's frame handle is a basic frame handler of the frame class located in the module Gadgets. So this frame handler in this base class does everything that's necessary to make frame fully functionable. So what we're going to do here is only do our own stuff that is necessary for dealing with the features, the special features of our fractal frame, namely all the fields that all are only dealing with the fractal specific stuff and not with the frame specific stuff. Everything that is only frame specific can be forwarded to the Gadget's frame handler procedure. So this is the reason why you see this Gadget's frame handle call here in every fork that is dealing with something that is not of any interest for us. Okay, it's also very important that you always provide an else fork, because else means that everything you are currently not thinking of and that you maybe also have forgotten will be injected here and also forwarded to the Gadget frame handle. It's likely that you will forget something and your whole Gadget will crash because a message is sent that is not properly processed. Okay, and this, what comes up here is an outlook for the stuff of the next video. We have two more very important message types. One is the attribute message and also the file message. The file attribute message is the part of the message handle that deals with everything in the gadget that's an attribute. Attributes, as I hope you will remember, are all those properties of a gadget, which is entirely an object, that can be made visible and also changed with the Columbus Object Inspector. For example, value fields or background colors, also the size of the gadget. All this can be changed because this is not just a property, it's an attribute. Attribute messages are processed differently, and I have a own function or an own procedure for dealing with attribute messages, and this is handle attribute. This we're going to do in the next video. And the same is very important, file message. A file message is something very interesting. It's a thing that is responsible for the persistence of the object. When you, for example, have this fractal inside a panel, like we did in the last video, and you store the panel, and everything in the panel is stored. And when this is done, also this file message is sent to our fractal, and this message means, please Fractal, we're now gonna save everything here in our panel. Please take care that you save all your contents by yourself. You're responsible by yourself. That needs to be reloaded when the gadget is rebuilded, namely when the panel is newly, freshly loaded. And this is quite a cool feature, because the message provides something on the file handle that's already open, and you can really store and also retrieve all the information that are specific here in this fractal. For example, the background color, for example, the plot color, for example, the dimension of the scales and the dividers. All this stuff can be saved to disk and is automatically reloaded when the gadget is retrieved. This is also very cool. I'm going to show you this in the next video. Okay, the next here, copy message, is not very interesting, because copying is not something we're gonna do very often. We can skip this for now. And at least in the last else fork, we also implemented here a gadget's frame handle. As I said again, please take care of every possible message that might be sent to your gadget, and take care of it. If you don't know what to do with it, then forward it to the base class, which is here gadget's frame handle. Okay, that's all for now. Thanks for watching, and